cryptographic points and directions. First, we talk about these fundamental concepts, several fundamental concepts in material science. First concept is crystalline. Maybe you have heard of this term on crystalline. And crystalline means that the atoms are suited in a repeating or periodic array over large atomic distance. That is, long-range order exists such that upon solidification, the atoms will position themselves in a repetitive 3D pattern, in which each atom is bounded to its nearest neighbor atoms. So this phenomenon is typical for metals, many ceramics, and also some polymers. And here we give you an example to show you this repetitive 3D pattern. Actually, this is a 2D because we just gonna give you the 2D, and you can just imagine we have a 3D, the third dimension, and inside this is a screen. So here this is the silicon oxide. Silicon oxide. This is this red dot called stands for the silicon atoms. This bigger blue dot stands for these oxygen atoms. When we have this silicon oxide, and we can see, and we have this is the repetitive 3D pattern, 2D pattern here. So for example, this is a hexagonal. This is hexagonal. So this is the crystalline silicon oxide. So this is whenever you heard crystalline, and you can just associate this crystalline with the repetitive pattern, or this is a periodic pattern. On the contrary, there is another concept called non-crystalline materials, in which atoms have no periodic packing. This occurs for complex structures and rapid cooling. And here I'm going to give you the same example, silicon oxide, but now this time it's called non-crystalline silicon oxide. And you can see here clearly, so this is not this repetitive 3D pattern. This is not a periodical pattern either. So amorphous equals non-crystalline. Whenever you hear this amorphous, it means non-crystalline. Amorphous, currently there is very, very important this material, bulk metallic glass. This bulk metallic glass, this is metallic, this is metal, but when people solidify, this is when people cool the molten metal to get this solid metal, and the cooling rate is very, very high. Because of the high cooling rate, so we finally get this is amorphous amorphous metal. That's the reason we call bulk metallic glass. And I will talk about this one later in our class. And then we talk about crystal structure. Crystal structure is defined as the manner in which atoms, ions, and molecules are spatially arranged, the structure. So unit cells, this is another concept. Crystal structures are divided into small repeat entities. These are parallelepiped, or these are prisms, having 3 sets of faces. So metallic crystal structure, we talk about this metallic crystal structure, tends to be densely packed. And the reasons for dense packing for this metal, we are very familiar with this metallic crystal structure. The reasons for the dense packing include typically only one atom is present, so all atomic radii are the same. The radii are the same. I'm not talking about this metal alloy. I'm talking about the pure metals. Metallic bonding is not directional, and we learned that is not directional. The nearest neighbor distance tends to be small in order to lower the bond energy. Electron cloud shields the quarks from each other. This is the reasons why metals usually have the dense packing. And the metals always also have the simplest crystal structures. So in the following slides, I'm going to talk about several commonly seen the structures for metals. The first one is simple cubic structures we call SC. Okay, look at here. This is a picture. This is a hard sphere unit cell representation. So this is rare due to low packing density. Only this protein, only this pole has this structure, and these close packed directions are cube edges. This is cube edges. This coordination number equals 6. So this coordination number is a number of the nearest neighbor atoms. Okay, you can see, you can use this configuration to count the number of nearest neighbor atoms for any specific atoms here. You can see here, for example, for this one, so this guy has 1, 2, 3, 4, 5, 6. These 6 nearest neighbor atoms. This is the reason this guy's coordination number equals 6. Any questions? And this is called reduced sphere unit cell representation. This is called hard sphere unit cell representation, and this is called reduced sphere unit cell representation. So this is our first crystal structure for metals, SC. For this one, we introduce atomic packing factor. This is the concept, atomic packing factor. Atomic packing factor is defined as the ratio of the volume of atoms in unit cell. So this is unit cell, say, and divided by volume of unit cell. So this numerator is the volume of atoms in the unit cell, and the denominator is the volume of the unit cell. The difference between these two volumes is the empty, the space. So here is we assume these hard spheres. APF for the simple cubic structure equals 0.52. And how to calculate? And here is give you an example on how to calculate this one. So this is the SC. This is a simple cubic structure. This is 1, 2, 3, 4, 5, 6, 7, 8. So here is 8 1/4 sphere. Right. So this this 8. So this 8, and so this 8. Okay. So this 1, 2, 3, 4, 5, 6, 7, 8 in the back. So this 8, and they form a whole sphere. The whole sphere and equals. We know that whole sphere equals the cubic of this is the power 3 of this size length, which equals a. This a cubic, and then we calculate and how much. This is A3. So this for one item. I told you this is the 1, 2, 3, 4, 5, 6, 7, 8. This 8, 1/8 the balls, and they form one whole ball. One whole ball's volume equals 4/3 pi, and so this is the radius, the power 3. This radius equal for here. Radius equals 0.5 a. Of a is the length of this side of this cube. So based on this equation, we can get this is APF for IC equals 0.52. Any questions? So you need, after the class, you need to think about on how we calculate this numerator and denominator when we calculate this APF. If you understand this clearly, and so you will understand this concept very, very clearly. The second, this crystal structure is called FCC, this face-centered cubic structure, and face-centered. So this is this one. So here, okay, this is face on this is animation. There is no animation here. So look at this one. So look at this one. So this is called atoms touch each other along face diagonals. Along the face diagonals. Note, all atoms are identical, and I assume this is the pure metals. All atoms are identical. The face-centered atoms are shaded differently, only for ease of viewing. Right? So only for ease of viewing. They are totally the same, exactly the same. So here is, so they are contacting each other along the diagonal line. So here you can see 1, 2, 3, 4, 5, 6. I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8. 8 is behind. This 8, this is 8 1/8 balls. Right? In addition to this 1/8 1/8 balls, and we have 4 half balls. 1, 2, 3, 4, 5, 6. I'm sorry, 6 half balls. And so then we calculate this coordination number. So we can see for here, okay? So this here, you can see this is 6 face multiplied by 1/2, as I said, 6 half balls, and 8 corners multiplied by this is 1/8, and so this is the totally 6 multiplied by 1/2, 3, 8 multiplied by 1/2, 1, 3 plus 1, 4. Totally within this cubic, we have 4 full balls. Right? So this is very, very important for us to calculate this APF. And also, we know the coordination number of this kind of FCC, this FCC structure FCC equals 12. And you can imagine, given one specific item, and how to count the nearest neighbor atoms for this specific item, and you will know this number equals 12. So APF, atomic packing factor for FCC. I told you guys, so we still use the same equation, and the cube here. Okay, so this is a cube, and so this is still A, and so this is A here, A cubic. This is the denominator. For the numerator, and we know that we have totally 4 balls. These are 4 balls here, and each ball we have 4/3 pi, and then this radius of this ball. Okay, the radius of ball multiplied by this power 3. So the relationship between A and the radius is very, very important, and we need to know and how to calculate here. You can see here. So here is A, and here is also, and the length equals A. So as a result, this diagonal, the length of this diagonal line equals square root of A. And square root of A equals what? Square root of A equals this radius, diameter, I'm sorry. So that means, let me use this is radii, one radius, second radius, third radius, and fourth radius. And so that means 4r equals square root 2a. And so that means r equals square root 2a divided by 4. So this is why we have this number within these parentheses. So based on this equation, we can calculate for the FCC the APF equals 0.74, which is higher than that for this is the SC. And physically speaking, it is understandable, right? So within this, this is a cube, and more space is occupied by these atoms. Any questions so far? As I said, when we talked about SC, and you after the class, you need to think about by yourself on how we calculate this APF. Once you understand this fully, so you will remember almost forever. Okay, so so understanding is very, very important for have long-term this memory. And the third, the structure is called body-centered cubic structure, BCC, FCC, BCC. So BCC atoms touch each other along cube diagonal, along the cube diagonal, not the face diagonal, along the cube diagonal this time. So note, all atoms are identical. The center atom is shaded differently only for ease of viewing. And for I'm talking about this image, this from Dr. Anderson's textbook. So here is you will have the sphere representation. So we have the center. This is a whole ball, and then we have 1, 2, 3, 4, 5, 6, 7, 8. The eighth one is behind this full ball. And we have one whole ball and 1 8 and one eighth ball. So as a result, so for this cube, we have one center ball plus 8 corners multiplied by 1 eighth. Right? So this is totally 2 atoms within this unit cell. And so the coordination number of this BCC equals 8. And you can see here, right? So this guy, the center. So this guy has 1, 2, 3, 4, 1, 2, 3, 4, 8, totally 8 nearest neighbor atoms. So the basic the elements that have this kind of the structure include this is a chromium, tungsten, iron alpha. Iron is a special. It has multiple these crystal structures. So have alpha, beta, and I'm going to talk about this one in the following slides. Tantalum and this molybdenum, and so this is the kind of metals they have the BCC. Any questions so far? Okay, no question. We move on to the next slide. And also, we need to calculate atomic packing factor. Look at this is the picture. Okay, so look at this picture. First, we know and how this is the atoms they are packed together, and then we just calculate using the equation APF. Numerator, denominator. Numerator we still use a cubic. Okay, but the key is on how we establish the relationship between a and this is the distance of the a and the radius of the ball. And so here, so let's see how many. As I said, for this one we have 2 whole atoms there. The whole one whole atom inside, and 1 is the corners on this is the on these 8 corners, and the total you have the 2 whole balls within this cube. And so how to calculate establish the relationship between the radius and this A, and based on the definition of BCC, and these items they are packed along the cubic along the diagonal of the cube. And so that's the reason that it means that from here to here, the distance equals 1, 2, 3, 4, 4r, right? So this is 4r. You can see this 1r, this 1r. The whole ball has 2r. There's a 4r. 4r equals the diagonal length. The diagonal length, how to calculate the diagonal length based on A equals the 4r equals square root of 3 multiplied by A. We know that. So here is square root of 3A divided by 4. This is how we get this term within these parentheses. And so finally, here you can see this very clearly. And we can get this is the APF for BCC, which equals 0.68. And then we got going to talk about the fourth. This is a structure, crystal structure. So this is a special one. This is called hexagonal and close packed structure, HCP, hexagonal close packed structure, HCP. So you can see this one is different. Okay, so you can see on layer AB, and stacking sequence. This is a stacking sequence. So layer by layer by layer by layer. This is 3D projection. This is 3D projection. Here is A sides, and this is B sides. This A sides and B sides. This is repetitive. This is a 2D projection. So here is a layer. This is a top layer. So this is a middle layer, and bottom layer is a bottom layer. Okay, so you can see top layer and bottom layer. We have this is a shallow green and this is a deep green. And so you should know that based on here, if we use these two different projections, we can get a better understanding of this is a structure. And similarly, and for this is a C. Okay, this is a C. And for this is a cubic, and we can calculate that, and we have 6 atoms, whole atoms, and within the unit cell. As I talked before, please note that all these atoms listed here, and they are identical, and we use different colors, and for the atoms and also for the bond between these atoms, just for viewing purposes. You need to be very, very careful about this point. Otherwise, you will be confused. Because we are talking about metal, pure metal. So APF equals 0.74 is high, right? So this is for this kind of structure, we have this kind of CD, and this is magnesium and titanium, and this is Zn. We have these 4 typical metals and that have this HCP, the structure. So up now we have talked about the 4 different crystal structures. One is SC, the second one is the FCC, third one is the BCC, the fourth one is the HCP. And we talk about APF, atomic packing factors, and we talk about this is the coordination numbers, and for each coordination number for each of these 4 different crystal structures. And I would suggest that you review these lecture notes after class, and then think about how we calculate the APF, and then you will have better understanding of how these atoms they are packed in for all these cubic structures. Any questions so far? If there are no questions, I'm not going to continue, and then we introduce a new concept. This is theoretical density. So this density rho, and density rho equals mass of atoms in unit cell divided by total volume of unit cell. So this is the density. We know density, right? We know density is the weight per unit volume. So here is material science. In material science, we use mass of atoms in unit cell divided by the total volume of unit cell, the same thing. So for here, rho equals Na Vc Na. So we have this equation. So in this equation, Na is the number of atoms per unit cell. A equals the atomic weight, right? Number of atoms multiplied by atomic weight is the total mass of the cell within this cell. And Vc here, and Vc is the volume of unit cell, and volume of unit cell. And Na here is the Avogadro's number, and the Avogadro's number is a very huge number, and 6.022 multiplied by 10 power 23. So it means the number of atoms per mole. If you have taken this chemistry class in high school or in this the chemistry department and at our university, and you have better understanding of how what Avogadro's number is. If you have any questions, still have any questions, and feel free to my office, and then I will give you more materials and to refresh your memory Avogadro's number, or you just learn new things. So any questions? No question? No question. Let's move on to next slide. And I'll give you an example. We introduced one concept, then I give you an example on how to calculate this theoretical density rho. I'll give you one example, chromium, which has BCC crystal structure. So based on this equation, so this is the atoms per unit cell. This is the weight per mole, right? Weight per mole, you can see. This is mass per mole. And a cubic volume, and you need to divide it by these atoms per mole, because this is weight per mole, mass per mole, and so it's here. So this is, you need to divide by the atoms per mole, and then you can get. So this is a theoretical density. For chromium, A equals 52 the gram per mole. This, the atom is very, very small. If we calculate the mass or weight based on each of these atoms, that we always need to carry a very, very huge number, 10 power negative something, right? So that's the reason, and there's some very, very talented scientists, engineers, many years ago, they artificially generated this number, the mole, right? This mole is a huge number, which equals 6.022 multiplied by 10 power 23. A huge number, right? It's a huge number. You need to know that. So based on this equation, is R radius, nanometer. This is a nanometer here, right? And you can calculate this. A is this is nanometer, and then you just plug in all these number here, and then you can calculate. So you can just calculate the rho. This rho equals 7.18 gram per cubic per this centimeter cubic. So this is theoretical, this is actual. So some students might ask, oh, man, why is this difference? Yeah, what is the difference is that there might be some impurities. Right? So this is no matter how careful we are when we make this is the atom, nor we when the scientists make these kind of materials, and there is still a chance for the probability that they bring some impurities inside, or some corrosions, or some oxidation there. There's some change, but you can see it's very, very accurate already. The density of materials class. So in general, the density of metals is higher than density of ceramics, and this ceramics has higher density than polymers. Why? Because metals have close packing, metallic bonding, and often large atomic mass. The ceramics have less dense packing, often lighter elements. The polymers have low packing density, often amorphous, and light elements, for example, carbon, hydrogen, and oxygen. And so here, for this is the picture shows, and this picture shows the density for different materials. This is density. This is the ordinate. Abscissor's material ordinate is the density, and we can use metal and graphene, ceramics, semiconductor, and so these here zirconium. So this kind of material, and they have decent density, but for polymers is low. They have lower density. The composites they have a very, very wide density because, as I said, composites, and they are a combination of two or more fundamental materials, and that's the reason. And so the density of composites depends upon how many fundamental materials you combine them together and what they are. So that's the reason they have very, very wide density range. So composites have intermediate values, composites, as I said. And then we talk about polymorphism. What is a polymorphism? So two or more distinct crystal structures for the same material. Allotropy polymorphism. This is the titanium. For example, this is titanium. Titanium have the same element, but they have different alpha, beta, alpha titanium, titanium alpha, titanium beta, the carbon, diamond, graphite, and then going to talk about this is fullerene, carbon fullerene C, and 16 carbon 60, and it is just like a soccer ball, which has 60 carbon atoms, and also the fourth one is the carbon nanotubes. So this is I'm going to talk about this one when we talk about this is a carbon. And also iron system. For iron system, we can have this liquid, okay, based on the temperature. So this we have for the solid, we have BCC, FCC, BCC, and we can see we have delta Fe iron, gamma iron, and this is alpha iron. So these three irons, they have different crystal structure. Any questions so far? No question. We talk about the crystal system. This crystal system, unit cell. We talk about unit cell already, and the smallest repetitive volume, which contains the complete lattice pattern of a crystal. And we have for here, okay, we just show you IC, BCC, FCC along with HCP. So these are four basic crystal structures for metals. That is, and they are the cubic. But to be general, without loss of generality here, and we just have x, y, z. So this alpha, beta, gamma, and they are not necessarily 90 degree, right? So also A, B, C, they are not necessarily the same. So here, A, B, C are the lattice constants. So this slide shows the commonly seen is a crystal structure. You can see, so the first one, cubic. So this is what we talk about for metals. For cubic, A equals B equals C, alpha equals beta equals gamma equals 90 degree. And hexagonal, tetragonal, this is a trigonal, also the orthorhombic is a monoclinic, and triclinic. So this is the 1, 2, 3, 4, 5, 6, 7. This is the 7 crystal structures. And then we talk about the point coordinates. The point coordinates for unit cell centers, are half A, half B, and half C. For example, this is the cube. This is the cube. This is the cube. The unit cell. And so for the center, the cell center, it equals half A, the coordinates, half B and half C. If we divide this number by the respective the length, and we have 1/2, 1/2, or 1/2. Do you have sense? So point coordinate for unit cell corner, here is 1, 1, 1. So you can see 1, 1, 1. So translation, integer multiple of lattice constants, and we can get identical position in another unit cell. So this is just to tell you the position, because the XYZ coordinate system, and this one is used here artificially. As long as this is integer multiple of lattice constants, will result in identical position in another unit cell, because this is periodic arrays. It is a periodic pattern. And then we talk about crystallographic these directions. On crystallographic direction, and so we can see here, okay, so I'm going to show you. So for example, the algorithm, the vector reposition if necessary to pass through the origin. So here is the origin, and read of projection in terms of unit cell dimensions A, B, C. Read all projections in terms of unit cell dimension A, B, C. Adjust to smallest integer values. Enclose in square brackets, no commas. For example, UVW. Here is an example to illustrate for any generic point within this unit cell how to get this guy's direction. For example, here, so this is the middle point of this vertical side. So this is, we know that, right? So this is x, y, z. X is equals 1, y 0, z 1/2. You understand, guys? This is our first step. And then adjust to smallest integer values. Smallest integer values. And we just multiply every number by number 2. By number 2. By 2. So this will have 2, this 0, 1/2 becomes 1. Become 2, 0, 1. And then we can just put this 201 within this brackets, within this bracket without this comma, we have 201. Any questions? Okay, if you do not have questions, I'll be very, very happy. That means that you understand this concept very, very clearly. So in our first quiz, and I'm going to test your understanding of how to calculate this crystallographic direction. What? So second example is a minus 1, 1. Minus 1, 1. So this is a over bar represents a negative index. A negative index. This is x, y, and z. So this one, right? This is y, this is z. So this guy's coordinates equals minus 1, 1, 1. And then we write this guy as 1 bar 1 1 because this is the direction does not have negative value. If we have negative value, we just delete this negative sign and put a bar on the same number. So we have this result. Families of directions, we use the angular brackets UVW. So here is give you example, several examples how to calculate. So this is the crystallographic directions. So I suppose this is the origin x, y, and z. So here, okay, this is here. X is 1 on the front surface. Y equals 1/2. Z equals y equals 1/4. I'm sorry. Z equals 1/2. Here, this is the front line. So all of these guys we multiply by a common, and this is a multiplier by a value of 4. We can change all these guys into an integer 412. This is for this direction. And for this direction, you can see for this direction, right, for this direction, so you can see there's A, B, C. Right, so for this direction, we have x and 1/2. Y is going down now, right? So this is going down, y, and this is going in the negative direction, and -1, and z also going down 1/3, and then we multiply negative 1/3, and then we multiply by all these numbers by 6. We can have 3, 6 bar, 2 bar. And the one thing you need to remember, if this direction goes in the opposite direction of any A, B, or C, you need to denote it as the negative. So this is because this is our coordinate system we established for this is a cubic. So keep in mind, if the direction goes in any opposite direction of A, B, C, or X, Y, Z, and you should know that, and you should have a negative sign there. And you just treat this is the starting point of this direction as the origin, and that will be okay.